In this video, we are going to discuss discrete random variables along with their probabilities. So our first objective here is to distinguish between discrete and continuous. So if we first, let's start, what is a random variable? A random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Random variables are typically denoted using capital letters such as capital X. So keep that in mind. So that would represent the random variable. We will use lowercase letters then to list the possible values of the random variable or the sample space of the experiment. So for example, if capital X is representing the number of siblings that our statistics class has, that each student in our statistics class has, then lowercase x, the possible values of that could be 0 or 1, 2, 3, 4, and so on. All right. So we know that there's two types of random variables, and those would be discrete random variables or continuous random variables. We will be working with both, but today we're going to talk about discrete. So just remember the difference between the two is a discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with space between each point. So here if we have our number line, then you would just plot on those numbers. You're not including any of the values in between. So think of it like stairs. You're counting each step you go up. You can't stop right here in the middle of the step. You have to go from one step to the other. So an example here is the number of A's earned in a section of statistics with 15 students. So our random variable capital X would represent the number of A's, and then lowercase x could be 0, 1, 2, 3, all the way up to 15, all 15 students having A's. A continuous random variable has infinitely many values. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion, so that means it contains all the values in between. All right, so think measuring. So my example here is the speed of the next car that passes a state trooper. If capital S is representing the random variable speed, then lowercase s would be any value greater than 0. All right, so someone could be going 42.4 miles per hour. All right. So here in this example 1, we're going to determine whether the random variable is discrete or continuous, and in each case state the possible values of the random variable. So I encourage you to think about these yourself a little bit and then see if you are getting them right and understanding them. So A, the time it takes for a light bulb to burn out, that would be continuous. The time it takes could be anything greater than 0. All right, the weight of a T-bone steak would be continuous, and the weight could be anything greater than 0. So you could have a 10.5 ounce T-bone steak. All right, so you're not just going from 10 to 11, it could be anything in between those as well. The number of free throw attempts before the first shot is made, that would be discrete. And our possible values is we could make it on the first one, we could make it on the second one, we could make our first one on the third one, and so on. In a random sample of 20 people, the number with type A blood. Well, we're talking about the number of people, so that's going to be discrete, but think about the values. If I randomly sampled 20 people, I could have 0 that have type A blood, I could have 1 of the 20, or all 20 people could have type A blood. So it would be 0 through 20 as our potential values. Part E, the number of defects in a roll of carpet. That would be discrete. And the values that could be is we could have 0 defects, 1 defect, 2, 3, and so on. Part F, the distance a baseball travels in the air after being hit is going to be continuous. And that distance is going to be anything greater than 0. The number of points scored during a basketball game, that's going to be discrete. And while we hope that it's not 0, it could be 0. It could be 1 point, it could be 2 points, and so on. Okay, now realistically, there's probably a cutoff, all right, but you never know what the cutoff could be, because you have teams that can score in the 80s consistently. You have teams that have scored in the hundreds. So really, it could be any countable number starting with 0. And then the last, the square footage of a house is continuous. Now, while if you're ever house hunting and you look, when it's advertised on something like Zillow, you're going to see a countable number as a square footage, like a 1,540 square foot house. You're not going to see the probably in between, but technically anything greater than 0 would be possible values. All right, our second objective here is identify discrete probability distribution. So the probability distribution of a discrete random variable capital X provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, graph, or a mathematical formula. So suppose we ask a basketball player to shoot 3 free throws. Let the random variable capital X represent the number of shots made. What are the possibilities of lowercase x? Well, the possibilities, if the random variable is the number of shots made, this basketball player could make 0 of them, 1 of them, 2 of them, or all 3 of them. So those would be our possibilities. So consider this probability distribution. So it gives us our possibilities here, and the probabilities of each of those possibilities. So how do we denote and read these values? Okay, well, P of X is representing the probability that the random variable capital X equals lowercase x. All right, so that is what P of X is representing. So notation wise, you may see this written as the probability that lowercase x equals 0 is 0.01. The probability that lowercase x is equal to 3 is 0.51. So the probability that the random variable x equals 3 is 0.51. All right, so some rules for discrete probability distribution, not anything new actually. If you remember, the sum of all of the probabilities occurring have to add up to 1, and the probability of each individual event has to be between 0 and 1 included, so it could be 0 or it could be 1. So here, example 3, determine whether the distribution is a discrete probability distribution. If not, state why. Well, we needed to satisfy those two things in order for it to be a discrete probability distribution. So looking at part A, I'm looking at each probability here, and each probability is 0.2, so it does satisfy the fact that each probability of the random variable x equals lowercase x is between 0 and 1. So the next we want to know is the sum of all of those probabilities equal to 1. And if you add up 0.2 5 times, you are going to equal 1. It satisfies both. So yes, it is a probability distribution. For part B, something should stand out right away, and that is that we have a probability of negative 0.15. So this does not satisfy the fact that each probability needs to be between 0 and 1. So it is not a probability distribution. And then for part C, if we're looking, each probability is between 0 and 1, so it does satisfy that. But if you add all of those probabilities together, the sum of all of them is not equal to 1. So that would not be a probability distribution. Alright, so example 4 here, determine the required value of the missing probability to make the distribution a discrete probability distribution. Well, they all have to be between 0 and 1, which so far they are, and they all need to add up to 1, so if there's one missing piece, we're just going to take 1 minus the sum of the rest of them. So that's 1 minus 0.7. So the probability that x is 4 has to be 0.3 in order to make that a probability distribution. Alright, objective 3, graph discrete probability distributions. So we're going to graph the probability distribution from example 2 and then state what the distribution shape is. So example 2 was the free throw one. So just to have that table in front of us so we can refer to it, we had lowercase x being 0, 1, 2, or 3. Our probabilities were 0.01, 0.10, 0.38, and 0.51. So we're going to make our positive x and y axis like normal. Alright, x values is representing the number of made or successful free throws. So that could have been 0, 1, 2, or 3. And then our y-axis is representing the probabilities. I'm just going to go by 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. Alright, so the probability of the 0 free throws being made is 0.01. So we go up and we just make a straight line. And our straight lines are because the fact that it's a discrete probability means there's no values in between. So that's why we use straight lines. Okay? So 1, there's a 0.1. Oops. 2 free throws was 0.38. And then 3 was 0.51. Alright, so that would be the graph of our probability distribution function. The shape, if you look at that, it's tailed off on the left-hand side, so we would say that this is skewed left. Alright. Moving on to objective 4, we're going to compute and interpret the mean of a discrete random variable. So one semester I asked a small statistics class of 10 students to disclose the number of people living in their households. I obtained the following data. So there's what we call the raw data. Okay, it comes straight from the sample. Create a table to show the probability distributions. Okay, well I see my smallest number is 2. We could have 3 people, 4 people, 5 people, and the largest number is 6 people. We know there's 10 students, so those that have 2 in their household is 2 out of 10, which is 0.2. Those that have 3 in their household is only 1 person out of the 10, which is 0.10. 4 people is 3 out of the 10, 0.3. 5 people is 3 out of 10, which is 0.3. And then 6 people in their household, 2 students out of the 10 said that, which would be 0.2. So when we create our table here, we have our possibilities of the random variable and the probabilities of that. So we have 2, 3, 4, 5, and 6. And then our probabilities are what we just found out of the total. So really, we have done this before because those are just the relative frequencies. Okay, we just took the how many we had out of the total. So there is our table. So then in part B, it says calculate the mean number of people living in the 10 households. Well, when we have the raw data, we can find the mean. The mean is just the sum of each individual data point divided by the total number in the sample, capital N. So we're going to take 2 plus 4 plus 6 plus 6 plus 4 plus 4 plus 2 plus 3 plus 5 plus 5. Divide that by 10, and that is equal to 4.1. So the mean number of people living in the 10 households is 4.1 people. And if we kind of break that apart, we can get to this formula that's on the top of the next page for you. I'm going to go back and verify it, where we can use the discrete random variable probabilities to find the mean. And this is great if we don't have the raw data, or if we're working with a lot of values in our raw data. So the mean of our random variable x is equal to the sum of each value the random variable takes on lowercase x times p of x, the probability of x. So let's go test that up here. We have the sum of x times p of x. So if we do that, I'm going to take 2 times 0.2 plus, I'm going to take 3 times 0.1 plus, I'm going to take 4 times 0.3 plus 5 times 0.3 plus 6 times 0.2. And if you type that into your calculator and do that math, you do get a mean of 4.1. Okay? So it does matches up. Now sometimes it will be a little different, just because, you know, when we have probabilities of something, we're rounding things and we're not using the raw data. So it could be slightly off, but they are they're the same thing. Okay? So we're going to be using that formula quite often here. So example 7, calculate the mean of the discrete probability distribution presented in example 2. So that was the free throw one. So we're going to take the sum of x times p of x, which is going to be 0 times 0.01 plus 1 times 0.10 plus 2 times 0.38 plus 3 times 0.51. And you do that and you get 2.39. All right, so that, I guess we're going to interpret here next. That is the mean, and that's for the made free throws. So what that means is if we repeated the experiment, of shooting 3 free throws many times, then we would expect the number of free throws made to be around 2.39. Okay, so the probability of doing that once, okay, that's what happened when we, ran that experiment or whatever. If we repeat that experiment over and over lots of times, then we would expect the number of free throws made to be around that. It's obviously not going to be every single time, but we know the more we do something like the law of large numbers says, then the closer it gets to that theoretical or actual probability. It's a similar idea here. It's going to approach that mean of 2.39. So because the mean of a random variable represents what we would expect to happen in the long run, it is also called the expected value, which is denoted E of x. Okay, so if you are asked to find the expected value, you're just being asked to find the mean of the random variable. All right. Okay, so objective 5 says to interpret the mean of a discrete random variable as an expected value. So here in example 8, the graph of the discrete probability distribution represents the number of rooms in rented housing units in 2017. So part A, what is the probability that a randomly selected rental unit has 5 rooms? We're finding the probability that lowercase x is equal to 5. So 5 rooms, its probability is 0.198. Part B, what is the probability that a randomly selected rental unit has 5 or 6 rooms? So we're finding the probability that lowercase x equals 5 or lowercase x equals 6. So really we're just finding the probability that x is 5, or, which means we're going to add, plus the probability that x is 6. So if we look at 5, that's 0.198. 6 is 0.103. We add those together and we get 0.301. Part C asks, what is the probability that a randomly selected rental unit has 7 or more rooms? So we're finding the probability that x is greater than or equal to 7. And in our case, it only goes up to 9. So really, we're just finding the probability that there's 7 rooms, plus the probability that there's 8, plus the probability that there's 9. So looking at those numbers, we're going to take 0.039 plus 0.018 plus 0.008, which totals 0.065. So if a rental unit is randomly selected, how many rooms would you expect the unit to have? So remember, your expected value is just equal to the mean of the discrete random variable. So we're going to take the sum of each variable times its probability. All right, so we have 1 times 0.009 plus 2 times 0.017 plus 3 times 0.217 plus 4 times 0.391 plus 5 times 0.198 plus 6 times 0.103 plus 7 times 0.039 plus 8 times 0.018 plus 9 times 0.008. You do that and you get 4.355, which will approximate to 4.4. So what that means is we would expect a rental unit to have 4.4 rooms on average. All right. Example 9 here. A term life insurance policy will pay beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose an 18-year-old male buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, the probability that the male will survive the year is 0.998937. Compute the expected value of this policy to the insurance company. So we want to know, what do we expect the insurance company to make or lose, I guess. So they could profit or they could lose money. Interpret this result. Okay, let's talk about our goal is to find the expected value of x, which would really be the mean of the random variable, which is the sum of x times p of x. So we need to get the probability distribution table so that we can use those values. So if you think about this, there's two possible outcomes. I guess let me set up the table. We got two possible outcomes. That would be that the male survives or that there is death. Okay, so our two outcomes: survives or death. Okay, so we need to figure out, well, what is the x value when that occurs? Okay, so let's let x, we like to denote our variables, let capital X be a random variable that represents the payout. Okay, so that would be to the insurance company. So that means the insurance company is either has money lost or gained. And that depends on the survival or death of the person that's assured. Okay, so we know that the probability that the male survives, well, the probability that that there's death is just the complement of that. So the complement that someone survives would mean that there is death. So that means the probability of surviving plus the probability of there being death has to equal 1. So we know the probability of surviving is 0.998937, which means the probability of death, if we take 1 minus that, would be 0.001063. So those are our probabilities that we can fill in here. We got 0.998937 and 0.001063. So now we need to determine what's our possible payouts. What are the possible X values when a person survives or when there is death. So if we think about this, if the male survives the year, then the company profits $350 because the male paid $350 for the life insurance, didn't die, no life insurance, so they just profit the $350. If there's a death or the male dies, well, the company gained $350 from the buy-in from the assured person, but then they have to pay out $250,000, which means the company ends up losing $249,650. So those are our potential values of our random variable X. So we have $350, or we have negative $249,650. So that means our expected value, which is the mean of our random variable, is going to be 350 times 0.998937 plus negative 249,650 times 0.001063. So that would give us an expected value of $84.25. Okay, so remember that is a long-term average. Okay, so the insurance company expects to make a profit of $84.25 on every 18-year-old male that they insure for a year. Okay, but that would be over a period of time. All right? Okay, so our third objective here is to compute the standard deviation of a discrete random variable. So we have standard deviation of a discrete random variable, capital X, is given by these two formulas here. I'm going to be using this one because I think it's easier to work with. You could by any means decide to use the other one, but with this one, notice we're taking this part here is almost the same as the mean, but the values are squared, and then this is just the expected value or the mean squared. All right, so in example 10, Powerball is a multi-state lottery. The following probability distribution represents the cash prize of the Powerball with their corresponding probabilities. So notice you just have grand prize. We don't have anything for the grand prize because that is a value that changes just depending on, what it is. Okay, so it could be a a 1 million gram prize. It could be a 350,000 gram prize. It just depends. So since that changes, it just says grand prize. So in part A, if the grand prize is $15 million here, so now we know the price or the prize of 15 million, find and interpret the expected cash prize. If a ticket costs $1, what is your expected profit from one ticket? So our expected value is going to be the mean. So we're taking the sum of x times p of x. All right, so we would take 15 million times 0 point, that has 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 6, 8, 4. Plus, we would take 200,000 times 0 0.1, 2, 3, 4, 5, 6, 2, 8. Plus, we're going to do that for all of them. And our last would be 0 times 0 0.972682422. Okay, so if you went through and typed all of that into your calculator, you would get an expected value of 0.299591659, which we will round to the nearest cent. So that's like 30 cents. It would be your expected outcome, rounded to the nearest cent. Okay, so the expected, over a long period of time, if you continue to play this, the expected cash prize would be 30 cents. All right, so think about your expected profit then. Is you pay $1, so you're losing $1, but then your expected cash prize is 30 cents. So really, you're expected to not profit. You're expected to lose 70 cents over a long period of time if you continued to play the Powerball. All right. So part B says if the grand prize is the 15 million to the nearest dollar, what is the standard deviation of the cash prize? What does this value suggest? So our formula for standard deviation of this would be, yeah, you're good. This would be the square root of the sum of x squared times p of x. And then we would subtract the mean squared. So this is where this one's nice to use, because if you just typed everything in your calculator, you can go back in and insert squareds. So we're really taking the 15 million times that probability of 0.12345678684 plus, you can do that, well, this is squared, sorry, and you're going to do that for all of them, so then it goes up to 0 squared times the 0.972682422, and then you're going to subtract our mean squared. So that was 0.299591659 squared. So when you do that before taking the square root, you're going to get the square root of 1,550,373.04, which is approximately 1,245. So that is your standard deviation, which suggests a large spread of payouts. All right. So remember, the larger your standard deviation is, the larger the spread of the money is, and that makes sense looking at, your chart. You go from a grand prize of 15 million. The next highest is 200,000, all the way to not winning anything. So part C, to the nearest million, how much should the grand prize be so that you can expect a profit? Assume nobody else wins so that you do not have to share this grand prize. All right, so let's let G represent the grand prize. So we want the expected value minus our $1 pay-in to buy the ticket to be greater than 0. So we're going to use our expected value formula. So we're going to take the grand prize, which is G, times the probability of winning the grand prize, plus, you're going to do that for all of them again, all right, so if you did that, you're going to get your grand prize times that probability plus everything else. If you did all that in your calculator, 196991659 minus your $1, you want that to be greater than 0. So if you add your $1 over and then subtract your 0.19699, you're going to get 0.1234567 times the grand prize to be greater than 0.803008341. Oh, I didn't finish. Let's see. Divide both sides by that probability there. So you would need G to be greater than $117,398,880.30. So really, you need your grand prize to be about $118 million in order for you to have a profit over the period of time. So if you keep buying to win the Powerball, then you would want it over the grand prize to be over 118 million, or to be about 118 million. So last part, does the size of the grand prize affect your chances of winning? Okay, it does not affect your chances. Okay, the size of the grand prize does not affect the chance of winning, provided the probability remains constant. All right, so it's not your probabilities changing, it's the potential grand prize that is changing, and over an amount of time, you can make a profit, but in reality, the probabilities are staying the same, so your chances of winning are not any different. All right, and that's what we have for discrete random variables.